All right, welcome back. So in the previous section, we looked at two particular infinite series that we were going to check the convergence of, and not only that, when it does converge, we're actually going to find what it converged to, right? By looking at first the geometric series, and then looking at telescoping series. We were able to not only know that it converged, but also what it converged to. Very often with many sequences, we will not have an easy way of knowing if what the sequence will actually converge to, but rather we're going to be interested in asking the question, does the series converge? Does the series converge? And so over the next few sections, we're going to be developing a bunch of different tests that we can apply to infinite series to help us determine whether or not it converges. We need lots of different tests because unfortunately there is no simple test that will always give us a definite yes or no. Okay. So the first test that we're going to be talking about is called the divergence test. Now before we get into the actual divergence test, we're going to make a little notation note. When we write sum of AK, what we mean is an actual infinite series now. We use this as a shorthand. This would be the sum as k goes from 0 or whatever starting value it needs to start at. Some will start at a different value than 0 of the AK, right? It's an infinite series. So we use the notation here, sum of the AK without any indexes on it at all, to indicate the infinite series. And that's just a convenience thing. So we don't have to keep writing k equals 0 to infinity. We use this as a kind of a shorthand. So with that in mind, we can now state the divergence test. The divergence test. We say if the infinite series converges, then this must be true, right? The limit of the underlying sequence has to be 0. Has to be 0. If it converges, then the limit of the underlying sequence has to be 0, right? The terms that we're adding up have to be approaching 0. Otherwise, we have no chance of converging, right? Because infinity times 1 over 10 is going to be infinity. Infinity times 1 over a billion is still going to be infinity. So the terms have to be approaching 0. That is a necessary condition. We kind of mentioned that before. Now I state it as kind of a general fact. Now, we can take this statement here, if the sum converges, then the limit goes to 0. And we can actually write it in an alternative form, which is probably more useful for the divergence test. Alternatively, we could say if the limit as n goes to infinity of a sub n is not 0, then the infinite series diverges. And that's the divergence test. Divergence. That's the divergence test right there. We look at the limit of the underlying sequence to see if it goes. If it doesn't go to 0, we know it diverges. Now, again, we've stated this previously, just because the underlying sequence goes to 0 doesn't mean that the sequence will converge. So when we take the limit of the underlying sequence and we get it equaling 0, we can't say it converges. What we would have to say there is it's inconclusive. But if it's not 0, then we definitely know it diverges. Definitely know it diverges. So limit going to 0 is a necessary condition for convergence, but it's not sufficient on its own. Turns out it has to actually go to 0 quick enough. And again, that's kind of a generic way of saying it. What we mean is what we meant, when we're talking about same idea of infinite, or improper integrals. Integrals going to infinity, right? 1 over x squared gets close to 0 quick enough that the stuff on the end has a limited amount to it. Whereas, as we saw, 1 over x did not get there quick enough. Did not get there quick enough. Okay. Same thing with some of our other examples there. Okay, so that's what also matters. That's in addition to the limit going to 0, it also has to get to 0 quick enough. Okay, and that's what our different tests that we're going to be using a little later on are going to help us do. Okay, so that is the divergence test, and we're going to be looking at some examples to check whether something diverges or not, or whether we can't tell.